Good morning, everybody. Thank you for attending this webinar this morning. I am Richard Potzer, education specialist from Impact, and I do the physical sciences, and physics and chemistry are my passion. I hope that you will learn something this morning, and let us just give it a minute or two. I see that learners are still busy logging in onto the system. So let us just see. All right, while you're waiting, you can see on the right-hand screen, on the right, there are handouts this morning. It is an exam paper that you can work through, but more about that later on. Okay. Okay, let us just start. Okay, as I said, I am a Richard Potzer education specialist for physical sciences, and okay, before we go on, let me just go through a few things, a few basics, so that we can, if you cannot hear me, make sure that your audio is on and your speaker volume is turned up. You will automatically be muted when joining this session, and I'm not going to answer any questions during the session. Please make sure that you write your questions in the box on the right-hand side or below. You can see there are a space for where you can for questions. So make sure that if you do have any questions, recommendations, comments, you're more than welcome to put it there. Okay. You will, or if you do have any other questions, you can send an email through to Impact by using the email address academics@impact.co.za. And if you are or info@impact.co.za, the YouTube and the handouts will also be available on the guided learning platform, Impact Learning platform. So yes, make sure, and you can also look at the webinar after this session on the YouTube, on Impact's YouTube channel, or recordings of the session. If you want to look at it again, you can send an email to Impact to get the YouTube channel link if you cannot log onto it. Okay. All right. I decided to do this morning a part of the chemistry that you will be assessed on in the June prelim and end of year exam. I'm not sure if you're going to write the June exam, but in any case, in the prelim and end of year exam, there are stoichiometric calculations that you need to do, and it's work that you did in grade 10 and 11. That you are also assessed on in grade 12. So if this is new to you, and if you doesn't understand some of the work that I'm doing here, you can look at the webinar, go for questions, and not all of it will be assessed, but it can be in a question paper. So so make sure that you do know it, or in any case, all the terms that are it was in previous papers. So make sure that you do understand it. So that are quantitative aspects that we're going to look at, and stoichiometric calculation. But the basic concepts you already know. All right. The basic concepts are the atomic number, the mass number, the element. The most important one is the mass number that's on the periodic table that can be found at the bottom, the key in the periodic table, on the periodic table at the bottom of each element. All right, and the term isotope is just a term that I know you know it already by this at this stage. So make sure if you're not knowing it, just go through it again. Okay, I include the periodic table again so that you can, if you're not, uh, so that you can use it. Okay, so you can see here the approximate relative atomic mass. That are the number that you're using in calculations. So that's the number that you will be familiar to by this stage, but make sure that you know when to use it. Okay, quantitative aspects that we're going to cover this morning are the mole concept, the relationship between mole mass and molar mass, the composition of compounds, the crystallization of water crystallization, percentage composition, the different formula, the molar volume of gas, concentration of solutions, percentage purity and yield, the limiting and the excess reactants. The reason why I'm doing this morning is because you use these calculations in stoichiometric calculations that are in your papers. And I do have a lot of learners that ask me questions, send through questions about the question papers and send, ask me where did they learn that, and they're not aware of this and that. So if this is new to you, please go for it with me, and if it's not, it's just then revision to you. Okay, the mole concept. I got a piece of carbon this morning for you. All right, this piece of carbon I weigh, and this is 12 grams of carbon. 12 grams of carbon is 1 mole. Okay, so this is 1 mole of carbon. Carbon is charcoal that you use for bright light. For bright light, so yes, that is carbon. So yeah, and this is why 12 grams is because of the 12, the relative atomic mass of carbon, and the mole definition is according to 12 grams of carbon, because each and every element on the periodic table, if you put it in grams, because remember the relative atomic mass don't have any units. Okay, so if we put it in grams, it's 1 mole. All right, so if you can see 12 grams will be 1 mole of carbon. 63.5 grams of copper will be 1 mole. 32 grams of sulfur. Sulfur is 1 mole. 201. All these elements are on the periodic table, and these are the relative atomic masses. All right. The Avogadro's number is a constant that's also on your formula sheet that you need to use when they ask, if there's a question to calculate the number of atoms, molecules, ions, then you use the Avogadro's constant. It's also a formula on the formula sheet where N is the number of mole, the capital N is the number of particles, and then you have Avogadro's constant. When you know when you have to calculate this is when they ask how many molecules or how many atoms or how many ions are there in a specific compound. Then you need to know that you need to use this formula. All right, this is a simple calculation of where the mole is given, and you need to calculate the number of molecules. Okay, so the next one that I do have here is the number of ions that form when you have 170 grams of sodium chloride dissolved in water. So when you do have, again, this type of question, determine or calculate the number of ions, you must know you have to use Avogadro's constant in a calculation in any case. Okay, in this question you do have not the number of moles, you do have the mass. But in Avogadro, in this calculation, you need the number of moles, not the mass. So what now? You first need to calculate the mole. And the way to do that is to consider and first figure out what is the number of moles that you do have here. So sodium chloride do have 2 ions, okay, because it's asking the number of ions. In the sodium chloride formula, you have 2 ions, sodium and chlorine. So in this equation, we can see that 1 mole of sodium chloride will give 1 mole of sodium plus 1 mole of chlorine. And therefore, we can state that 1 mole of sodium will form 2 mole ions. Okay, we'll have or consists of 2 mole ions. All right, so here we have the formula N equals M over N. So the mass given divided by the relative for the molar mass divided, and you have 2 moles. So now you know that you have 2 moles of sodium chloride when you have 170 grams of sodium chloride. Okay, so what I did, I take sodium. This is normal salt that you're using in the kitchen. That is sodium chloride. And I weigh 38,5 grams of salt here. That is 1 mole of salt. That is also, it's consider it's the same number of ions in here. That's in here. Okay. Here are atoms. Here are ions in here. Okay. So now we have 1 mole of salt, 1 mole of carbon. So, but if I just say the number of particles in 1 mole of carbon, you can say, all right, the number of particles, okay, they will be 6,023 multiplied by 10 to the 23rd particles. But now I am asking ions. There are 2 mole ions. So there are 2 ions in this formula. All right, so that's why we need to multiply it by the number of moles that you calculated. So we have 4 mole, and therefore then you can calculate the number of ions. Okay, so the relative atomic mass, formula mass, molecular mass, molar mass, these are the 2 that you are using. Remember, there's a difference in a formula. Formula is just, it's the same thing, it's the same number, you calculate it the same way. It's just we cannot say that this is a molecule because it's not a molecule. It's not an atom either. So we need to state that this is a formula. This is a formula mass. So we're talking when it's an ionic bond, we talk about a relative formula mass. So, and when it's a covalent bond, as in water, we talk about a molecular mass because it is a molecule that's formed. When we have water, it's a molecule. All right, so now we have stated that. So what is the molar mass then? It's the same calculation that you do here, and we just use the unit gram per mole. All right, how do you do it? You just take the relative atomic mass of each element, you add it together to get the formula mass or the molecular mass, and it's the same thing. We just use the unit gram per mole when they ask the molar molecular mass or the molar formula mass or the molar atomic mass. It's the same thing. All right, so what is the relationship between these 3? To calculate the number of moles, you need mass and the mass of the substance and the molar mass. All right, in this, they ask what mass of iron sulfide is formed when 5,6 grams of iron is completely reacted with sulfur. So now they ask the mass of the sulfide, and they're giving the iron. Okay, so first thing that you need to calculate, we find the number of moles of the given substance, you first calculate the number of moles of the iron. Okay, so the number of moles of the iron is 0.1 mole. So if there's 0.1 mole of iron, then it will also be 0.1 mole of iron sulfide. In order to get the mass of the iron sulfide, you need to calculate the mole, use the same formula. Then you have 0.1, multiply it with the molar mass, molar formula mass of the iron sulfide to get to the mass that you need here. Okay. So what is the relationship between these two formulas? The formula for mole and the formula for mole when we're using Avogadro's constant. Yes, when we're using the masses, the different masses. The mass of the element, if you need to calculate the mass of the element, you can manipulate the formula that's on the formula sheet and use mass equals the mole multiplied by the molar mass. All right. So, but if you need to calculate the moles, then you just use the formula as it is. The same here. If you need to calculate the moles of the element, you need the number of the atoms of the element, the number of particles, divided by Avogadro's constant to get the number of moles. If you need to calculate the number of atoms or molecules or ions, you need to have the number of moles. But if you still have to calculate the number of moles, you can also just use the same formula and just include your formula for the number of moles in your formula. It's not necessary to do it by part, but can I advise you that you, in any case, that you do the calculations apart, so that for the simple reason that if you make a mistake with the one, that you will lose not all the marks. All right. So how many relationship between the two of them? So why and how do you know when this will be asked? If they ask how many molecules. So how many molecules? Say you need to use that formula. If they give the mass and not the moles, you need to calculate the moles first before you can calculate the number of molecules. Okay, so your clue here is how many molecules, that formula. Mass given, first calculate the moles before you do the calculation. All right, so the composition of compounds, the water crystallization, you need to calculate that. So what is water crystallization? It's the simple thing is there's a difference between an hydrated crystal and a anhydrous crystal. Your hydrated crystal do have water molecules in the crystal in order for it to look like this. But if there's no water inside, then it looks like it's just like a powder, like very light blue powder. And that is anhydrous. This is an anhydrous copper sulfate. That is a hydrated copper sulfate. All right. So what is the formulas of hydrated compounds contain a fixed number of water molecules. So you will find that the copper sulfate, the hydrated copper sulfate will have 5 molecules of water, while sodium carbonate will have 10 molecules of water. All right, so it differs for each and every salt. So make sure that you do know the difference between them. You cannot just change it. Okay, so that is a fixed number. So your general formula for your chemical formula for water crystallization is salt and a dot between the salt and the water. This, learners, this is not a multiply. That just means it includes the water in the formula. All right. So the chemical equation that you do have is for your hydrated copper sulfate is copper sulfate plus your water molecules give you a copper sulfate with the water included. Okay, this is the hydrated, the formula for the hydrated. The anhydrous one is where you just have the copper sulfate. All right. There are certain steps that you have to follow. I included here. Here is a question or an example how to do this. This is a student. The student, as you know, chemistry is all about scenarios, chemistry and physics. So you have a student here that the mineral rosenite contains crystals of hydrated iron sulfate. And the student wants to find the value of the water of crystallization. So she wants to derive, or she wants to see how what is the value of X. She uses this apparatus to remove and collect the water of crystallization from a sample of iron sulfate crystals. So here you do have the iron sulfate crystals. So it is a hydrated iron sulfate crystals that we do have here. That she heats, and then the vapor, the water vapor collected here, cool down in an ice bath here, and salt mixture, ice and salt mixture, it is just to increase or have colder ice here so that the water vapor cools down easier, and there you do have the water. So what now? You do have the formula. You have a hydrated iron sulfate. You want to know what is the iron, what is the water part, what is the X. Okay, these are the students' results. So she has the mass of the tube before she put in the iron sulfate crystals. After she put in the iron sulfate crystals, it was 17.56. So if you subtract the mass of the tube from the 17.56, you will know what was the iron sulfate crystals, the mass of the iron sulfate crystals. So the mass of the tube and contents after heating to constant mass, that is 15.76. So after she heated it after a while, she found that it stayed constant at 15.76. So then she decided, okay, that's done then. All right. So the mass of the anhydrous iron sulfate equals 3.80 grams. Okay. It is what is being, if we look back, we can see the 15.76 is after it is being heated, minus the mass of the tube, So the mass of the anhydrous sulfate is 3.80 grams. Okay. The mass of the water is, if the two, you do have the hydrated iron sulfate minus the anhydrous iron sulfate, then you know that the mass of the water was 1.80 grams. Okay, so now we have to find the ratio here. So what is your next step? Your next step is find the chemical formula of the hydrated iron sulfate. Why do you have to do that? In order to get the mole ratio. So first, the iron sulfate, get your relative atomic masses of each, multiply it with your oxygen is 4, so you need to multiply it by 4. So your relative formula mass is 152, and here you have the relative molecular mass is 18. So when we have the amount of, or the number of moles of iron sulfate, it's, you use your mass that you of anhydrous iron sulfate divided by your molar mass, there it is, and it is 0.025, and the amount of water in moles here is 0.1 mole. Now you can calculate the mole ratio, and for calculating the mole ratio, where do we get 4? We get 4 by dividing the 0.1 with 0.025, because your mole ratio is 0.025 to 0.1. 0.025 divided by 0.025 is 1. 0.1 divided by 0.025 is 4. Therefore, we do have x equals 4. So your formula for the hydrated iron sulfate will be iron sulfate plus 4 and not plus and 4 water. All right. So the other one is percentage composition. You have to derive the percentage composition. So how do you do that? With your formula mass of element divided by mass of compound. Say, for example, we started with water, so the mass of percentage of an element. What do we have here? The sum of the percentages should be 100. So you must make sure that the percentages should be 100. If you have, you calculate the molar mass, the molar mass of water is 18 grams. You know that the mass of hydrogen is there are 2 hydrogens, so it's 2 multiplied by 1, so it's 2 divided by 18 multiplied by 100. So the percentage of the hydrogen is 11.11%, and the percentage of the water of the oxygen is 88.89%. So if you have to change it to mass, you can say in a 100 gram sample there will be 11.11 grams of hydrogen and 88.89 grams of oxygen. Okay, what I do have here is how to calculate the percentage composition of sulfuric acid. It's another example. You can just go through this example. It means you start with the formula, you calculate the molar masses, and from that you calculate also the molar mass of sulfuric acid, and you use the mass. The mass is divided by the sulfuric acid. So this is the molar mass divided by the molar mass of the sulfuric acid multiplied by 100 to get that percentage. So again, in a 100 gram sample, 2.04 grams will be hydrogen, 32.65 grams will be sulfur, 65.31 will be oxygen. But it's also the percentages if you need to calculate the percentage. All right. So what is the empirical formula? It is the simplest ratio in which elements of a compound bond with each other. This is actually something that you do each and every day. When you're writing formulas, you write the formulas for, say, for example, sodium sulfite. So you need to calculate the if we see what is the what compound contains 36.5% sodium, 25.4% sulfur, 38.1% oxygen by mass. So the same way that you did in the on the previous slide, you calculate the different masses, which mass. Okay, what they give here, you do have here 36.5 gram divided by the molar mass of sodium to get the mole. 25.4 gram divided by the molar mass is 0.79, and 38.1 gram divided by 16 is 2.38. Okay, so now after that you derive the mole ratio, and from the mole ratio, you know what's the formula. All right, so by writing formulas, if you don't know what the subscript must be here, you just do the empirical formula. All right, so what I do have here is the empirical formula and the molecular formula. Sometimes you will see this formula and then you will see that formula. And when you look at it, you will see, okay, that if I divide this with 2, then I will have CO2H. All right. So what is the difference between the two of them? The one is the empirical formula and the other one is the molecular formula. So what is the molecular formula? This is the actual ratio of the atoms in the molecule. This is the simplest whole number ratio. So again, you calculate the empirical formula first before you can calculate the relative empirical formula. Okay, why do you have to use that? In this example, again, the percentages were given and you get to the mole ratio to get to the empirical formula. And after that, if you have the relative formula mass of the compound is 90, you can derive them, calculate the molecular formula by getting the ratios again. 90, if the ratio is what we do have here, we see that the relative molecular mass of CO2H is 45. So now you know the ratio will be 90 to 45. So the ratio is 2 to 1. So the mass of the molecular formula is twice that of the empirical formula. So therefore you multiply each one with 2. Remember, if there's nothing there at the subscript, it's a 1. So that's why we say 1 multiplied by 2 is 2, 2 multiplied by 2 is 4, 1 multiplied by 2 is 2. All right. So the molar volume of gases, you know the formula, it's also on the formula sheet. This is at STP. STP means stand temperature and pressure. It's 22,4. This is a constant number. So this is the formula for molar volume calculations. Again, always start with a balanced equation, have a mole ratio for the balanced equation, and after that you can state if you do have the mole ratio, you can after you have the mole ratio, you can just do the multiply it with the molar gas volume at STP to get to the number of the volume of each gas that you do have here. All right, it's only with gases that you do have the molar volume of gas calculation. All right, so the concentration of solutions. What are the concentration of solutions? Is, say for example, if you want to dilute fruit juice concentrate, you want a certain concentration. Okay, it must not be too sweet or too, I cannot even taste what is in it. Okay, so what I did this morning, I do have a question here, and the question that I do have 200 moles of water. As you can see, there's the two. You can just see it. Okay, 200 moles of water. Some of it evaporates. Okay, I put in some more water. So now you can see we do have, okay, 200. Right. So, and I measured 5,85 grams of sodium chloride. So we know that 58,5 is 1 mole. Can you see that? And this is only slightly, this is 5,85 grams of sodium chloride. So this cannot be 1 mole in any case. Right, just for interesting fact. All right, so I'm going to put the water in a glass. I'm going to make a solution with a certain concentration. Okay, there's my 5,85 grams of salt and dissolving into the water. Okay, this is a certain solution that we do have here. Okay, dissolved all of it. All right. So, all right, I see there's some salt in the left in the glass again, still, but it's not. So, what will the concentration be of this? Okay. Let me just see if I can place. I'm not into salt water, but okay, there is salt in it, but I will not taste it when I put in one more of salt. Okay, it would definitely not. Oh, all right. So what will this then be? So we have to calculate the concentration of the solution that I made just here. So how are we going to do it? Calculate the concentration. What do you have? You have mass and you have volume. So the volume must be in cube decimeters. If you do the calculation, it must be in cube decimeters. So you have to change it from cube centimeters to cube decimeters. Okay, so by doing that, you have to divide with 1,000. So I divide the 200 cube centimeters with 1,000, and that is 0.2 cube decimeters. Okay, and I have mass. Now, in my formula, there are two formulas. You can calculate the concentration. The one is C equals N over V. That's the mole divided by volume. The other one is concentration is mass divided by molar mass multiplied by volume. The calculation that we are busy with now are in the paper that I put, that's a handout today. So you will see in the stoichiometric calculations in the paper that you have to calculate the concentration of a sodium hydroxide solution. So this is what you're going to use and how you're going to do that. So write down what you do have and what is asked. Okay, so in order to do the concentration, you need to calculate the number of moles. Do I have the number of moles? No, I have mass. Okay, so now you look at your other formula that's also on the formula sheet. Mass divided by molar mass volume. Where do I derive the molar mass from? I can calculate the molar mass by adding the relative atomic masses of the sodium and the chloride. I find this on the periodic table. Okay, so by finding this in the periodic table, added together, I do have the molar mass of the sodium chloride. Now I can do my calculation by dividing the mass given with the molar mass multiplied by my volume to get to my concentration. All right, so how do I know what formula to use? Just look at the two formulas, see write down what is given. Okay, the moment you write down what is given, it's just easier. Okay, then you have to do percentage purity calculations. Not all of the questions are in each and every paper. So please, learners, make sure that you can do this if this is in a paper that you will be able to do it. It's a very simple, this formula is not in your formula sheet, so it's something you need to learn. The percentage purity is the mass of the pure product divided by the mass of the impure product. Okay, so you have a 150 gram sample of copper ore contains 87.3 grams of pure copper. So it's just a simple calculation by using the pure copper divided by the impure product multiplied by 100 to get the percentage purity. Okay, so here are an example of how to do this, but this is stoichiometric calculations. The previous calculation was very easy, so that's easy. But how do I know now? Now I ask you, if the mass of calcium chloride produced is 3.6 grams, what is the percent purity of the limestone sample? Now, okay, percentage purity, do I have the mass of the pure product? Do I have the mass of the impure product? They ask the percentage purity. If the mass of calcium chloride produced is 3,6 grams, okay, what is the 3,6 grams? Oh my goodness, I'm not sure. Okay, now where do you start? Okay, limestone is mostly, read your question. Limestone is mostly calcium carbonate. Jake wants to know how much calcium carbonate is in a sample of limestone. The sample will be your impure product. Okay, he finds that the sample weighs 3,5 grams. There's your impure product. Okay, he then adds concentrated hydrochloric acid to the sample. Why? The equation for this reaction. Why? If the mass of the calcium chloride produced. Now you know the mass of the calcium chloride, but I want to know what is the pure calcium chloride. But they gave me the calcium chloride produced. So what do you know? What do you want to do? You must know what was the mass of the calcium chloride. Okay, so the number of moles of calcium chloride that form, remember, the ratio is 1 to 1. So if I do have the number of moles of the calcium chloride, I will know what is the number of moles of the calcium carbonate used in leakage. All right, so that is by calculating the calcium chloride, the number of moles of calcium chloride, then you can multiply it by the molar mass of the calcium carbonate to get to the mass that you need for the mass of the pure product. Okay, so after that, you can just do your calculation. That is a type of question, stoichiometric calculation that you need to do. Okay, then theoretical yield versus actual yield. That is a question that can be asked, especially in practicals. And if I'm not, yes, it's the term 3, practical that you need to do with the circuit diagram. There are a question about the actual yield and theoretical yield. So make sure that you do understand that what is theoretical yield versus actual yield. Theoretical yield is the amount of product we should produce from the complete conversion, and your actual yield is the amount of product that is actually formed. So your actual yield must be given within the problem or measured during an experiment, while your theoretical yield must be calculated. Okay, so here is a question again, how to do the calculation for the percentage yield. Okay, you have sulfuric acid that reacts with ammonia to produce the fertilizer ammonium sulfate. What is the theoretical yield of ammonium sulfate that can be obtained from 2 kilograms of sulfuric acid? It is found that 2,2 kilograms of fertilizer is formed. Calculate the percentage yield. Where do you start? Always, with calculations, start with a balanced equation. All right? You do have the formulas here. The formulas will not always be given in a scenario like this. So you have to write it on your own. You have to make sure that you can write the balanced equation. So we do have the sulfuric acid plus the ammonia, and the salt form is ammonium sulfate. How do you know that? Because NH3 will form, in order to form a salt, this must be a positive ion, and that will be ammonia. So it will connect with the hydrogens that we do have there. All right, so then you calculate the number of moles of the given substance. So here are the different steps that you need to follow to get to the percentage yield. How do you know that? Because you need to calculate the actual yield over the theoretical yield. You first, why? You first, what is the theoretical yield of ammonium sulfate? So the theoretical yield of the ammonium sulfate you first need to calculate. Okay. So how do we get to the 2,2? That's the actual yield. 2,2 is the actual yield. All right. So you first need to get to the mole, to get to the mass, to get to the theoretical yield. All right. To get to the ratio of the balanced equation. So make sure that you do understand. If you go through this calculation, make sure that you do understand. I just want to say to you, in a question paper, we normally ask it in we will say, write the balanced equation, or if we didn't say that, we will say calculate the number of moles of the given substance. So there will be a way of following the certain steps, but in this scenario here, in any case, you need to know and understand what type of questions you need to do before you can do the percentage, what type of calculations you need to do before you do the percentage yield. Okay, the limiting and excess reactants in a what is the limiting one and what is the excess? The limiting is the reactant that is completely used up in a chemical reaction, and the excess reagent is the reactant that is not completely used up in a chemical reaction. In this combustion of methane, we have a balanced equation of 1 mole of carbon of methane will react with 2 mole of oxygen molecules to form 1 mole of carbon plus 2 mole of water. 10 molecules. So here we do have 1 mole of methane, 2 moles of carbon of oxygen molecules form one carbon dioxide molecule and 2 water molecules. All right. So what is the limiting and excess reactants in the combustion of methane? If I say to you that we do have five molecules, or 5 mole, if we do have 5 and we have 8, which one will be the limiting and which one will be the excess reactant? We're talking about reactants here. We're not talking about the products. So you're ignoring now the products here. So for 5, we know the ratio is 1 methane to 2, 1 mole methane to 2 mole oxygen. If I have 5, I need 10 mole of oxygen. There's only 8, not 8 here. So what is the limiting reactant? The oxygen will be the limiting reactant. What is the excess reactant? The methane will be your excess. All right. So the limiting reactant will make sure that you don't. If we look at this reaction again, we will see that if we recall the balanced equation, that is the balanced equation. Our balanced equation, if we look at the limiting reactant, the theoretical yield and the percentage yield, the combination between the 3 of them. Our balanced equation for the combustion of methane implies that every 1 molecule reacts with 2 molecules of oxygen. So when we have 8, in this reaction, we have the same thing. We have 2 to 1 ratio. So we need 2 oxygens for 1 carbon dioxide molecule. All right. So 8 will form 4. So which one will be if we have 5, only 4 will be used. So this will be in excess. There will be an excess of methane. They will only form 4. So which one will be the limiting reactant? The oxygen. The least amount of product that will be formed is the 4 carbon dioxide. So we have enough methane to make 5 carbon dioxide molecules, but only 4 carbon dioxide molecules form. So therefore, your oxygen will be the limiting reactant. The 4 carbon dioxide molecules is a theoretical yield, and the methane is in excess. So that is the type of questions that you need to understand and need to do in stoichiometric calculations. Here are all the formulas that is necessary for you to use in, okay, sorry, there might be a C for concentration. So these are the formulas that we're going to use for our stoichiometric calculations. What I did here is I put it in three sections for you. If mass is given and mass is asked, if mass, so that is the, if mass is given, the first one is mass and mass calculation. So the scenario is calculate the mass of oxygen obtained when you have 29.4 grams of potassium chlorate. It composes completely to potassium chloride. First thing, you have to write the balanced equation. How do you know what is potassium chloride? You know chloride. The formula for chloride is ClO3 negative. So potassium is in group 1, so that's why it's a 1:1 ratio. So the formula will be potassium chloride from 2 potassium chloride plus 3 oxygen. Convert all the masses to mole by dividing by the molar mass. So the mass given is the 29.4 of the potassium chloride. So you have to calculate you have to form the mass that is given to get to the moles in order to work out the mole ratio of each one. So you use the balance equation to calculate the moles. So you know now you have the balance equation 2 mole. What is asked? The oxygen. So we want the oxygen. All right. The mass of the potassium chloride is given. So you know 2 mole potassium chloride will form 3 mole of oxygen. So 0.24 mole will form 3 multiplied by 0.24 mole divided by 2 will give you the number of moles. Okay, so convert the number of moles of the required oxygen to gram by multiplying by the molar mass in order to get the mass that is formed. All right, the other one is mass volume calculations. Here you have a sample of limestone, you have a mass, and they ask the volume of gas formed. All right, so now we have mass. Again, balanced equation, convert mass to mole, determine the number of moles, convert number of moles to volume. If it's at STP, you can just multiply by 22.4. All right, so make sure that all of the calculations that I stated at STP before you can just multiply by 44.8. All right, volume calculations, that is just a ratio calculation, and that is an easy calculation where you have to state, they state here, calculate the volume of oxygen required to convert 300 cubic decimeters of sodium dioxide completely to sodium trioxide. Okay, and the volumes are measured at the same temperature and pressure. That must be the statement, or else you cannot just state that they are equal. Right, so write the balanced equation. You start there. Determine the volume of the required substances. So by writing the balanced equation, you know that 2 mole plus 1 mole gives you 2 mole. All right? So 2 cubic decimeters plus 1 cubic decimeter will give you 2 cubic decimeters. They're asking the number of oxygen if we do have 300 cubic decimeters of sulfur dioxide. Okay? So the ratio is 2 to 1. 2 cubic decimeters to 1 cubic decimeter. So if it is 300 cubic decimeters, it will be 150 cubes oxygen needed. All right. So volume calculations. If they're given it in cubic centimeters of hydrogen and cubic centimeters of oxygen. So again, write the balanced equation. 25 cubic centimeters of hydrogen, 20 cubic centimeters of oxygen are mixed, and an electric spark passes through the mixture. Steam is formed. hydrogen and oxygen. How do you know what the balanced chemical equation will be? Hydrogen gas plus oxygen gas forms this, and it forms steam that will be water. So you start with your hydrogen gas, your oxygen gas, and your water, and then just balance it. Okay, so now you know 2 mole, 1 mole, 2 mole. That's your ratio. So your ratio will be the same for your volumes, 2 volumes, 1 volume, 2 volumes. Okay, so if we do have here in cube centimeters, 25 cube centimeters will react with 12,5 cube centimeters. Okay, and your yield will be 25 cube centimeters. All right. So the volume of oxygen left, all right, will be 20 minus, this is what we have, and it will react with the oxygen. Okay, there are 20 cube centimeters oxygen, but only 12,5 cube centimeters will react with your 25 cube centimeters. All right. So what will be left of the 20 cube centimeters? There will be 7,5 cube centimeters left. All right. So in your container will be the 7,5 cube centimeters plus the 25 cube centimeters that are the yield. Okay. And therefore, your total volume of gas left in the container will be 32,5 cube centimeters. Make sure you do understand it. And then again, I include the additional resources for physical sciences, the Docs Intra textbooks, the Quanta books, and the Science Clinic notes. If you didn't download the Science Clinic notes yet, please make sure that you download it from the website. It's for free. It's very easy to use and very comprehensive. And then if you want, they did start with the with webinars as well, so you can go on the website and register for that. Okay, and make sure that you use the Quanta textbooks. If you still don't, if there are still things that you don't understand, use your videos, look at the videos, and if it is grade 10 and 11 work that I discussed just now that you implement and apply in grade 12, make sure that if you don't understand it, that you go onto websites like Mindset, Learn.Mindset, or borrow grade 10 and 11 Quanta DVDs to look at the Quanta DVDs to see what this is all about. If there is something that's still bothering you, all right, you can also use your mind maps and question papers to along with your Quanta question book to prepare for your tests and exams, and go for your stoichiometric calculations in your notes so that you understand how they ask the questions and what they're asking the question papers. Right. So if you do have any questions, remember to send your questions to info@co.za or I can exactly. And if you're not registered with Impact and do want to know how to register, you can contact us at impact.co.za. Thank you very much for joining today's session. And have a nice weekend. Thank you for being patient with me, and yes, enjoy the rest of the weekend. Thank you. Bye.